All right, we're here at the shop at Badass Racing Engines. This is where we build the motors for some of the nastiest cars on the street and some of the fastest cars out at the track. Today we're going to be talking about heads, porting, and valve trains. You know, the heads and the valve train are the most complicated, misunderstood part of the motor. It's also where it makes all its power, and the characteristics are at of how it's going to run, where it's going to make its power at, and how it's going to act on the street or at the track. You know, years gone by, it used to be about high compression ratios and really high RPMs. These days it's not about that at all. It's more about cam profiles and head flow. The name of the game these days is flow and velocity. Let's look at heads right now. All right, we got a pair of typical heads right here, small block Chevys. This is a cast iron one, this is an aluminum one. I'm sure you've heard the myth about can't run aluminum on the street, it warps or it cracks or you blow head gaskets. It's pretty much all fake. We used to have that problem way back in the 70s maybe, but not these days. We'll get into that a little bit later. I'm going to show you the components of the head right here, just so you get a basic feel of what parts are. Some of you probably already know what it already is, and some of you might not, but I'm going to show you anyway, just so we can know where we're starting here. Up here we have, these are the rocker studs. These are screw-in ones. Factory heads have press-in studs. These right here are guide plates. They guide the push rods, keep them in line with the rocker arms. Right over here we have the intake ports. Sometimes these are called runners. That's what we usually call them, or intake runners. This area right here is the deck surface. This is where the head gasket seals against. These right here are the valves. This is an intake valve. This is the exhaust valve. Of course, the intake valve is always larger than the exhaust valve. On this side right here, we have an exhaust port. Sometimes we call that the exhaust runner also, but that's the exhaust port. And we're back again to the top right here where the valve springs are and the retainers and the locks. All right, what we have here are a pair of big block Chevy heads. Nothing fancy about these. In fact, they're just used up cores that I took out of my core bin just to show you the different characteristics between the two. Let's start with this one right here. This is your typical oval port head. Nothing fancy about this. It's a common head. It's not a very good head for performance. It's got the small oval ports. Let's look at this one right here. This head right here is a performance head. It's got the rectangle ports. These came off like the 427 cars and the 454s, things like LS6s, LS7s, things like that. Go back to this head here. This one has open chambers. What that means is the combustion chamber here is a lot more open, larger area. This head right here is a closed chamber head. Makes a lot more compression. But you have to be careful about the kind of pistons you use in these. You don't want to put an open chamber piston on a closed chamber head or the piston will smack the head. Looking at the ports right here, the rectangles, and looking at these right here in the ovals, later on in the tape we're going to get into porting. What you never ever want to do is try and port a set of oval port heads into rectangle ports. I've seen that come into the shop a few times. Some guys say, oh, I ported my heads to rectangle ports. Not a good idea. You either have rectangle port heads or you don't. It's not necessarily the shape here, it's the shape down inside the runner areas right there. Speaking of runners, they're all measured in cc's. What that means is cubic centimeters of water. The larger the cc's, the larger the area is in here, which means the more head flow. The way we measure head flow is in CFM, cubic feet per minute. We do that on a flow bench. We'll be showing you that a little bit later in the show here. Let's show you the casting numbers on these. This is how you tell heads apart. Lay this back here. There's a set of casting numbers right down here. We always go by the last 3 digits. Okay, this is where you want to look on heads. All heads have these, all the Chevy heads. Ford heads use dates. We'll get into that when we get into Ford heads. This one right here will have the same thing. This is what we're looking for right here. Here's a casting number right here. You can get a little tight shot of that there. We always go by the last 3 digits. So like these heads, we'll go back to the oval ports here. These heads right here, I believe are 882s. Oh, strike that, 820s. These are 820 heads. All right, as you can see right here, we have some casting numbers. I talked about before, it's always the last 3 digits that we go by, or usually in most cases it's the last 3 digits. This right here is a 186 casting. It's actually a real good casting for a small block Chevy head. This is a typical small block Chevy head, only I've modified it to go from stock to the next extreme, to the next extreme, to about as far as you can go in a stock cast iron head with all the modifications for performance use. I'm going to start with the top right here. This is just a stock configuration. What we have here are pressed in rocker studs. These aren't ideal at all for performance use. Reason being, anytime you have a performance engine, it means you got a performance camshaft. What that means is you got to have bigger valve springs. Well, the more valve spring pressure there is, the more it pulls up on the stud, and these pull right out, and you're done. So we'll get into that as we go down a little bit more. Here's the valve springs right here. These are a standard 1/250 size, 1 1/4 is basically what it is. You can't go very stout with those. That's a typical stock small block Chevy valve spring. That's about as big as you can go on those. This is the stock port right here, the exhaust port. They flow decently for being stock, but nothing great about them. Right around here we have the deck surface area. I showed you that before, and the valves. Intake valves always bigger than the exhaust valve. This is your typical configuration on a Chevy. Here again, here's the intake runner right here. Nothing fancy about it, just your typical intake runner. And we come back around here, and here's the push rod guide plates right here, or the guide holes right here where the push rods go through it. All right, this is the next one down here. This is also a stock configuration, but I've done something a little different here. This is the inexpensive way to hold studs in place. You can see right here, there's little holes drilled with a roll pin stuck in there. That's called pinning the studs. It's simply a drill bit and a kit that you can buy. It comes with a drill bit and some roll pins that come through. You drill through, and it stops the studs from allowing to pull out under high spring pressures. We went to a different seal here. This is just what they call an umbrella seal. It's a light years better than a factory O-ring seal, just for keeping the oil out. These are just the oil seals. All right. I'll show you this in a minute. This particular one is ported. We'll get to that in just a minute. I just want to go around and show you something here. This is the next combustion chamber. Same design, same everything as here. The difference is we've put hard seats in this one. And I have the same hard seats here down here so you can see. What that means is, you've probably heard about not being able to run unleaded gas on early heads and things like that. Well, what that means is there's a tungsten, some are powdered metal, some are tungsten. This is tungsten steel right here that's pressed into the exhaust part of the head right here. It's actually machined out, and there's a tungsten ring that gets pushed in there. If you look real close, you can probably see there's a little groove right here where it's been machined out. There's a little ring right around here that has been machined out, and a tungsten seat's been pressed in there. That keeps the valve from slapping into the cast iron. It slaps onto the hard tungsten. It doesn't wear out and doesn't recess the valve. It runs on unleaded gas. What's behind that is leaded gas used to have tetraethyl lead, and what that did was, lead's metal. It's a very soft metal, and as the spent exhaust gas would come back out here, the lead wouldn't actually burn. It stays metal. So what would happen is when the valve would close, instead of it slamming closed into the head, here's an example right here on the exhaust valve here, instead of it slamming closed, you get lead deposits in here and it cushions it so it doesn't recess the seat or recess in the cast iron. Unleaded gas doesn't have the tetraethyl lead, so there's nothing to really cushion the valve from slamming back into the soft cast iron head. So what we do is we install the hard seat in here, and then it's unleaded gas ready. We'll go back around the front here. On the next one down here, we've done the next best thing. These are actually screw-in studs. This is a very simple way to put screw-in studs in. It's a simple stud. We've simply pulled these out, run a 7/16 tap down inside here, and run a screw-in stud. The reason we do that is, again, because of the valve spring pressures on performance camshafts. You need a higher spring rate on a performance cam to close the valve. If you don't have enough spring pressure, the valve doesn't close fast enough, and the piston will close it for you. And that's not a good scenario. So by tapping these out and putting these in, they can't pull out. No matter how much pressure you have on them, it can't pull out. Around the corner here, same thing. We have a stock port here. I'll show you the porting in a minute when we go around. This again is a different chamber. This is fitted with a 202 valve and a 160 exhaust valve. I'm sure you've heard the term 202 heads and 160 exhaust valves. What that's referring to is the valve size. These right here are 194 valves. The 194 valve just simply means it's 1.94 inches across the face of the valve. One down here is 2.02 inches, rather, which is 2 inches and 20 thousandths of valve. That's why they call them 202s. What that means, it's just a bigger valve means more flow. Okay, in most incidences, more flow. More flow means more power, and more power is more fun. This is done on a stock runner here. We haven't changed that yet. Okay, and that's real common. A lot of guys put 202 valves and 160s in, and they don't port anything. You don't gain much by that. But again, we have 250 seats, which is 1¼ inch valve seats. So we'll go back around here again. We'll go down to the next one here. These are real screw-in studs, and the only way to put these in is to machine this boss off right here. It has to go on a mill or on a Surrey machine. We use a Bridgeport here. We mount it up and we cut the tops off. We actually shave part of this off and true it up, and that makes it all flat. Then we drill it and tap it and run a stud. Here's a stud right here, what it looks like. It taps in. It's got a shouldered nut right here. The reason that has that is it holds the guide plate in place. This is what's holding the guide plate. What the guide plate's doing is holding the push rods so they stay aligned with the rocker arms. If you have a rocker arm movement, the rocker arm tip over the valve won't stay aligned, and you push on the side of the valve and you can break the tip of the valve off. So it's important that the push rod guide plates are in place there rather than the stock ones that the factory uses. It's a lot more stable. This one here is also machined here. It's fitted with what we call a PC Teflon seal. There's two different types on here, just to give you a variance of what the two types look like. But they call them PC seals, which are really mean, they're Teflon is what it is. This one here, this is on a ported exhaust port, or a ported exhaust runner. For more flow, we'll come around here and show you the chamber. I just did a quick deburring on the chamber. This is not polished, it's just deburred. Nothing fancy about this. Some guys go crazy, you hear the term, man, my heads are ported and polished. That really doesn't mean jack. No one polishes heads on the street. No one that knows anything runs polishing on the heads on the street. We'll get into that later when we actually get into porting later on in this segment. But the reason it's deburred in here is it takes away hot spots. If you look in the chamber above it, you can actually see casting flash, and it's actually like little bumps. If you look at it under a microscope, it's like little mountains, and every one of these little peaks can become a hot spot. And under high compression engines and high horsepower engines, these things can act like a glow plug, and they can actually fire the cylinder before the spark plug does. It's called pre-ignition, and man, it does some serious damage to a motor. So what we do is down here, we've just taken a sanding disc on a die grinder and just cleaned it up in there, and it takes away any hot spots that you might have under high horsepower conditions or high heat conditions. Come around here, this one is ported. Again, we'll get more into porting a little bit later in the segment. But I just want to show you the difference between a ported intake runner and a non-ported. It's a lot more symmetrical. It doesn't look like it's much. It's quite a bit though. Let me show you here too. I'll come around just to give you an idea of what the porting is. Here's a valve pocket right here. This one right here, you can see it has a lip inside here. If you look real close, let me put this down and look right here. It's got lips inside here that are just factory casting flash. Get it in here. It's got factory casting flash in here where it's been machined out. The problem is airflow comes in here and it hits this and gets diverted to the center of the valve. We don't want it to go to the center of the valve. The valve's in the way. What we want it to do is come out and into the chamber and fill the cylinder up. That's how you get horsepower. The more you fill the cylinder, the bigger the bang. The bigger the bang, the harder the crank goes around, and that's the key to horsepower, is raising cylinder pressure. Like I said earlier in the segment, the key to horsepower these days is filling the cylinders, flow and velocity. Old school days, it used to be raising the compression and just revving the living crap out of the motor, and that just strains all the parts. We don't need to do that these days. We're making more horsepower on 9-to-1 compression today than we were on 12-to-1 compression of yesterday. And so we can get away with pump gas, and it just runs a lot better. So what's happened here when we do porting, as you can see, the ridges in here. I'll give you a size idea here. The valve is out in this location here. This is the seat out here. When you come in here, this barely fits in there. All right, when we come down here to one that's ported, I'll push this valve out right here. I can pull this one out. Look inside here. This has all been worked on inside, and you can see there's quite a bit of size difference there. And it's not necessarily the size. But let's go to the one above it. You can see this again. This barely fits inside there. It's tight. Come down here again. Lots of space. The idea is it's just a smooth funnel of air going on filling the cylinder. The whole idea behind this again is to flow more fuel and air into the cylinder. Well, what goes in must come out. Okay? So the exhaust ports are done also. We do this right here on the exhaust side. We'll push this valve out. Give you an idea here. Same thing inside here. If you look close up here to this one up here, grab my little pointer here. We can look in here. You can still see the same lips. And what that does is when the exhaust valve opens, it just doesn't want to direct gas out the exhaust port where it's supposed to go. So what we've done is come inside here and we've cut it up. You can see the hard seat right here. And if you look real close, you can see the parting line. There's a parting line right in here where the hard seat is at, where it meets the cast iron to the tungsten steel, and we've blended all that together. So when the valve opens, it's a nice smooth flow right on out, and the more you evacuate the cylinder, the more you can fill it again when the intake valve opens. You can put more burnable, fresh fuel and air inside there. If all the exhaust gas can't get out, then you got some left over in the cylinder, and when the intake valve opens again, you still have leftover exhaust gases, and that's not going to make much power for you. All right, the next thing we can talk about on this head are valve springs. Let me kick it around here and I'll show you. We talked about this before, that a factory spring is 1.25 inches. And I said it doesn't give you that much of a spring to use with performance cams. One thing, because the wire size here is not that big of a diameter, and also the travel on it. I mean, if you have a 550 lift cam and the spring compresses in what they call coil binds, it won't go down far enough to allow that kind of lift. You need to go to a bigger spring. Again, also RPM has a factor with it. You need a lot stouter spring if you're going to go up in RPM, where, like I said earlier, the spring can't close the valve fast enough and the piston will close it for you, okay? And that's what you call valve float. We'll get into that a little bit later too. On the next seats here, these again, even though we upgraded on the pins and everything, this right here is still 1.25 inches. The only way you can get away with these on 1.25 inches is to go to a conical spring. This right here is a conical spring. It's 1.25 inches down here, but you can see how it goes up to a larger diameter, which allows a larger wire to go in there. And this happens to fit right in the factory seat right there, okay? The next way up we can go from there is a series performance spring, where we actually cut the spring seat out. And if you look right here, it's already cut out right here. We went to a larger seat diameter, which allows the use of a monster spring like this. Fits right inside the seat, just like that. It allows a really high lift cam, high RPM, and just all-around better spring. It will close the valves for you at any given RPM. And keep in mind too, when you increase valve size, you increase the mass, the weight of the valve. A bigger valve, a 202, has more metal on it than a 194. And when you go to a 205 or a 208 or a 225 valve, that's a lot more mass on there. It takes more spring to close that valve. Okay, so anytime you increase valve size, increase RPM, and increase the lift of the valve by the camshaft, you need to close that valve faster. Bigger, heavier springs allow that to happen. So by cutting these spring seats here, it allows us to use a bigger valve. Let me give one word of caution. This isn't too early of a head, but when you get into the early fuelie heads, and I'll show you one of those in a minute, how to tell a fuelie head, or what they call a camelback head, when you cut valve spring seats on those, there's a water jacket right down inside here. And it's very common when you put a spring seat cutter in here to cut right into the water jacket, and that just ruins the head. Cast iron is really hard to weld on, and it's one of the disadvantages of cast iron head is once you've done something like that, it's pretty much junk. The cool thing with aluminum heads is you can TIG weld it back up, machine it, and continue on. In fact, we'll do that. We'll go on to the next head right now. That'll be the early camelback heads. All right, what we have here is a small block Chevy head. It's a little rusty because it came off my core pile in the back, but we're using it for demonstration purposes here. This is a camelback head, otherwise known as a fuelie head. The reason they call it camelback head is because right here there's a casting on the edge of the head here. It resembles kind of a camelback. It's got dual humps, and so it became known as a camelback head. It also became known as a fuelie head because on the early Corvettes they had a Rochester mechanical fuel injection system that they ran on those, and a lot of these heads came on those cars. This one right here is a 462 casting. I'll show you right here is a casting number right here. We always go by the last 3 digits again, 462. These are pretty popular heads. Camelbacks came in 461, 462, and 463 heads. That's a really good head to use for basic performance stuff if you're going to stay with a cast iron head. This one here has been set up, like I say, it's a little rusty. It's off my core pile. I did some work to it a while back and never got around getting back to it. I got too busy. This is my own stuff here. It's been set up, as you can see, it looks a little different from a factory head. I've already machined all the bosses off here where the rocker studs have been in. So what we set it up for now are screw-in studs and guide plates. And here's your typical screw-in stud, and here's a typical guide plate. So they've already been machined down and drilled and tapped. So the screw-in studs and guide plates can go in here. And that would allow the use of larger valve springs or a stouter valve spring for a higher lift cam and higher revs on the engine, and also the stability of the push rods being aligned up for the rocker arms. Now we're going to talk about the valve seats. I showed you before the hard seats, the tungsten and powdered metal seats that we use for protection against unleaded gas. This head right here is also fitted with those. You can see the tungsten seat right here on the exhaust valve and on the intake valve right here where the shiny metal meets the cast iron inside here. And again, what that's for is protection against unleaded gas, because leaded gas had the tetraethyl lead in it, and we don't have that these days. So there's no cushion when a valve slams shut. And the stouter the spring you use, the harder the valve slamming shut. So what happens is there's no cushion there anymore. So we have to use a harder seat. I just wanted to get a good clear view of that so you understood what that was all about. All right, what we have here is a pair of small block Ford heads. These are cast iron heads, nothing fancy. They were just stock heads. I did take the liberty of doing a few modifications to them just to give you some comparisons of what you can do to these heads. Just like the Chevy heads, we were talking about date codes and stuff and casting numbers. Fords use a date code rather than just a casting number. Here it is right here underneath here. It's D0OE. Ford uses a letter to designate the decade, and D is 1970s decade, and 0 would be 1970. If it was a D2, it would be a 72. We can look at this head right here. This is a 66 head, and we can tell that because it's a C6, the first two letters and numbers here. So C is 1960s decade, 6 would be the corresponding year. C6 would be 66. Let's look around here to this head. This is a typical problem with Ford heads. A lot of them came with non-adjustable valve trains. And how we can tell the non-adjustable valve train are by the rocker studs here. These have a 3/8 post area that presses into the head, but if you notice it necks down to a little teeny 5/16, and there's a shoulder right here, a tapered shoulder. That's for the rocker nut just to go down and lock on there. You torque it to like 19 foot-pounds, and that's all you get. I mean, there is really no adjustment. So a lot of times we'll modify these heads. We'll go ahead and cut them, cut the bosses off, and install screw-in studs or screw-in studs and guide plates, which gives us the allowance of an adjustable valve train, so we can adjust the rocker arms for different heights to get a correct valve train geometry. This particular head right here is one of the rare ones that actually does have an adjustable valve train. The way we can tell this is it has 3/8 press-in studs with a 3/8 threaded top on it. Ford only did this for a couple of years. Then they went to the non-adjustable. It's too bad they did that because it's hard to use good like aftermarket rockers or anything like that because everything needs to be adjustable. So even with these as it is, they are still pressed-in stud. They would either need to be pinned or pulled out and put screw-in ones in regardless if you're going to run a stout spring or if you want any kind of true performance out of it. Stock Ford heads aren't the greatest for performance. Reason we say that is because, let me take you over here to this side. This is the exhaust ports right here. You can darn near cover the whole thing with your thumb. I mean, there's not much there to breathe. If you got 289 cubic inches or a 302, or you got a stroker or a 332 or a 347, and you have these heads on it, you're not breathing much out of these little teeny ports right here. There's not much coming out of there. So obviously people want to fit with bigger valves. Well, they will fit them with bigger valves, but you know what they never do? They never enlarge the ports on these things. So the valve might be bigger, but these can only flow so much. That's not real good. So let's flip it around here and I'll show you what we've done to this head. These are some typical modifications people do to these things. This right here is your typical valve size. This is a 178 intake and a 145 exhaust. This is stock for 289s and 302s, all right? A lot of people will go and say, oh man, I got 351 Windsor heads on my 289 or 302. That's all fine and dandy, but I got news for you. The exhaust ports are exactly the same size. The intake ports are exactly the same size. They're the same valve springs. They're the same rocker studs. They're the same pretty much everything. The only difference is they got a little bit bigger valve. They got a 184 intake and a 154 exhaust. You're not going to gain much if you still have the exact same exhaust port size and the same intake port size. You really didn't go anywhere. I mean, it's not like it's going to make that much of a difference. All right, so what some people do is they'll put Chevy valves in. This right here has a 194 intake valve and a 160 exhaust valve. That's all fine and dandy too. You can put Chevy valves in Ford heads. The reason being is they all have 11/32 valve stems. Ford and Chevy uses the same relative length. There are slight differences, but the same relative length. And the same diameter on the valve stem size. They're all 11/32. So they will fit if you enlarge the valve seats. The problem with this is, and here's the big problem, anytime you put a bigger valve in a given size chamber, the valve area starts getting closer to the sidewall here, to the combustion chamber wall. Problem you run into with that is when the valve opens, we'll open it up here, it doesn't have much breathing right here. I can barely fit the screwdriver. In fact, I can't hardly fit the screwdriver through there. Where a stock valve, I do have room there. I can fit it through there all day. So fuel and air mixture coming into the cylinder has a chance to breathe around here. It can actually get through the side of the chamber. When you put bigger valves in here, it's putting the edge of the valve closer to the chamber. You're not going to breathe very much. You can't fill the chamber if it can't breathe on this side right here. You can actually put a valve so big in here that it comes so close to the side, you actually lose flow over here. So going to a bigger valve didn't get you anywhere. In fact, you can actually lose flow by going to too big of a valve. How we get rid of this is unshrouding. And what that means is we take a cutter when we do the bigger valves, we actually cut the edges of the combustion chamber out. As you can see, this one's cut right here. There's a little machine mark right here. And on the top side right here, you can see it around here. And just to give you an idea, we can open this and I can actually look at the space I have right here. I can actually move this around in here, okay? Compared to this one right here, I can barely, let me open this valve right here. I can't even get the screwdriver through there compared to this right here. Look at this. I can wiggle it around in here. That means that fuel and air can flow around this side. The valve is unshrouded. That fills the cylinder. What did I say the whole key to horsepower was? Filling the cylinder with more fuel and air makes a bigger bang. Bigger bang means more horsepower. Just sticking big valves in obviously doesn't get you more horsepower or a bigger bang because it can't breathe. I did show you the Chevy heads. Let's look over here to the Chevrolet head. We talked about this earlier, what I did to this. This is the first one we looked at. This one was unshrouded also. If you look down here, even the Chevy valves get an unshroud. All right, so when we go to a 202 and a 160 valve, we do cut the sides of the chambers so the valve can breathe, okay? All right, here's another set of Ford heads. I'm just going to give you a comparison to a 289-302 head that we were just looking at to the Cleveland heads. Back in the early 70s, the mighty Cleveland was the one to have, and I just want to give you a comparison of that and show you some new heads in a few minutes here that are even the next generation. As you can see, here's the intake ports right here of a typical 289, 302, or 351 Windsor head, pretty much all the same. You go to this right here, a Cleveland head, which is a canted valve head. If you look at the chambers here, the valves aren't side by side. They're a little canted off to the side a little bit. That's what we call a canted valve head. You look at the ports right here. This is a two-barrel Cleveland head. Port size, pretty good size, not bad. Great for street performance, it's not too big. But you go to the four-barrel heads. This is the Cleveland four-barrel. They came in 70, those type of era cars, 71, that type of era. You can see the massive port size on these things. This is very similar to a Boss 302 head. I'm sure a lot of you have heard about Boss 302s. They use those for racing purposes, and released them in a 69 and 70 Boss 302 Mustangs. They didn't last very long because the heads are just too doggone big for 302 cubic inches. I mean, the motors wouldn't come alive till about 4,500 RPM, but from 4,500 to about 9,000 RPM, those motors really rock and rolled. The problem is it didn't have much below that because the intake runner size was so big and the valve size was so big. I mean, these are almost 2¼ inch valves. They're like 219 inch, which is 2 plus 190 thousandths. It's pretty big. That's a lot of valve area. And when you have a little 3-inch stroke like a 302 motor, it just can't draw enough fuel and air through there. You need a longer stroke. Ford realized that and they went to the 351 and they dubbed it the 351 C4V, which stood for Cleveland 4 Venturi. Ford never used the term really four-barrel so much. They used the term Venturi. So a lot of these guys call the heads 351 C4V heads. But Ford did realize they had a problem with that, so they came out with the 351 C4V and also called another one the Boss 351, which came in some Mustangs and also Panteras, 71 through 74 Panteras when they were released in the United States. These are excellent heads for race use. Again, though, they're cast iron. They're really heavy. Not much use for these days. The Clevelands are kind of outdated. Some of you might disagree with me, but I'm the one that's running the race shop, and I tell you, we don't use these things very much. Cleveland style has gone out. They have just too much rotating mass for what's being used out there these days. I'll show you a couple of Windsor heads here, and you'll understand why. We'll go to those next. Okay, what we have here is a pair of Windsor heads. This is what we have in today's technology, and one of the reasons I said the Cleveland's a little outdated. Bigger is not always better. I mean, yes, the Cleveland heads are big. The Boss heads are big. They do flow big numbers, but bigger is not better when you're talking heads, and this is a misconception a lot of people have when dealing with valve trains and heads. You know, it all works together. Everything's physically working together. I mean, stroke is working with port size and valve size, and you got velocities going in there. Velocity makes volume, volume makes flow, flow makes horsepower, you know, but if you don't have the velocity, you're not going to get the flow. And too big of a runner or too big of a valve is not going to get you the velocity you need to make ample RPM or to get the engine to spool up fast enough. So with that, here's some Windsor heads that have everything and then some. This right here is a really good head, real good bang for the buck. This is an Edelbrock Victor Jr. We use a lot of these in our shop. This right here is a 210cc intake runner, which sounds big, but it's not even half the size of a Cleveland head. But it's plenty big for making big power. I mean, making 500 horsepower on a street motor on one of these is not that hard to do. We have 351 Windsors that make 500 plus horsepower on pump gas using these heads. It's a very fine head. It's 205 intake valve, 160 exhaust valves. These come in multiple chamber sizes, 60 cc's and 70 cc's are really good, so you can have different compression ratios. Again, the nice thing about aluminum, contrary to what you've heard before, Aluminum is repairable. It does not warp, it does not crack. Cast iron does warp and does crack. Race heads like this NASCAR head here is also aluminum, and they're that way for a reason. We can repair them. They're lighter. They run cooler. It's a real fallacy when you hear about people saying you can't run aluminum heads on the street, and that's just not true. Every import car out there has aluminum heads on it. Every American sports car, all the Corvettes, all the Vipers, all that kind of stuff, they're all aluminum heads, okay? So that just doesn't ring true with aluminum heads not being reliable on the street. Anytime you have aluminum, it wicks away heat a lot faster than cast iron. So you automatically get a cooler running engine. The combustion temperature inside the chambers right here is cooler. There's a rule of thumb that when you're running aluminum heads, you can run 1 full point higher in compression than you can over cast iron heads without detonating. So meaning, if you have a, say, 10-to-1 motor and that's running max on cast iron heads, you can go to a 11-to-1 motor running aluminum heads and still have about the same ability to run timing and the same amount of cylinder heat in the or the head temperature on the combustion chambers. Again, though, going too high in compression isn't that necessary these days. Let me give you an example of that. This is I haven't cleaned this one up yet. I'm still working on this. We're building a Winston Cup motor for a client of mine. This is a Robert Yates high port head. Excellent head. This motor right here dynos at, well, it did before we took it apart, dynoed at 678 horsepower at 9,000 plus RPM. And it did that on 9-to-1 compression. So 9-to-1, I mean, that's what your stock street car has in it. So that kind of gives you an idea. You really don't have to squeeze the heck out of the compression and make 14-to-1 or 13-to-1 compression to get any power. This thing makes almost 700 horsepower, like I say, on 9-to-1 compression. It's an awesome head. It's got raised intake ports. I mean, these are the stuff to run right here. I mean, this is as good as it gets. You're not going to get a finer head. They're canted valve, just almost like a Cleveland, because the valves are so big. They have to cant them to the side to be able to fit them in the chambers. These flow big numbers. They run a shaft rocker system, which is a good way to go. When we get into rockers in a few minutes, I'll show you about the shaft rockers. These happen to run a titanium intake valve, and they run a sodium-filled exhaust valve, which wicks away heat. And the titanium intake valve is very light, I mean, ultra lightweight, so it requires less spring pressure to close that heavy valve. We go around here, great big exhaust ports, almost as big as or I should say, slightly bigger than the Victor Juniors here. There's also a standard Victor head that's even bigger yet. They flow some big numbers too. If you're going to be supercharged or nitrous or something like that, a bigger aluminum head's the way to go. You can see the combustion chambers right here. Here's the big valves. These don't really need unshrouding so much like the other heads because you can see the angle here. The angle's laid out. It's really laid out. So when the valve opens, it can really flow around it. It has quite a bit of space here to flow out and fill the chamber. And mind you, it's not common or it's not uncommon for these motors to run at 9,000 plus RPM for an hour at a time. It's just that's the way they run around the track. And they're making between 650 and 800 horsepower, depending on if it's a Cup motor or a NASCAR motor. These are a fantastic head. These are also, like I say, every bit as good for street or for street strip or for just race use. We use them for both. Great big springs, 1.5-inch springs. We get enough spring height here to run some big cams. These allow lifts up to 650, 670 on the roller cams we use. Great big 7/16 studs, very stable valve train. If you run a 3/8 stud, the stud might wiggle around a little bit because the spring pressure is so great, and you got the push rod pushing up over here and the spring pushing up over here. It's really pulling on this stud, and it wants to move them around. So we run a very large stud here. Guide plates, nice shaped intake ports, nice combustion chambers, nice heart shape, spark plug relocated for a better burn in the cylinder. Everything about these is great. This technology here is very similar, same thing. Spark plugs are relocated, valves are located in a particular area, combustion chambers are designed for just maximum flow. And I mean, on a motor like a 351, these heads rip. All right, we're back to another set of heads here. Actually, these are some we just looked at. I just wanted to reiterate on a couple of points here and the importance of aluminum heads against cast iron heads. You know, for performance use and stuff, cast iron heads just aren't where it's at. I mean, you can port them, you can do all the modifications to them and stuff, and if you've got the time to do it yourself and do your own porting, which hopefully at the end of this series here, you'll be able to understand how to do that and do it yourself. But if you have to pay for it, and by the time you put all the money and effort into a set of cast iron heads, for a few bucks more, you can get aluminum heads already ready to rock and roll. I just want to reiterate on the aluminum, the importance of this, and the wives' tales that are floating around out there that just aren't true about aluminum cracking or warping or head gaskets blowing and stuff like that, because that's just not true. Really what the deal is with aluminum, aluminum is repairable. It does run cooler. You get a cooler combustion. It's lighter. I mean, a pair of heads on aluminum, aluminum heads on a motor, you're talking 40 to 60 pounds weight difference between a set of cast iron heads on any different given motor. Let me tell you a little problem they had with aluminum when they first came out, and this is probably where some of the wives' tales came from. When aluminum heads first came out, we were doing a machining process on them that was very similar to what we did on cast iron heads. If you look real close at this cast iron head on the deck surface here, this one's already been machined. I already cut this one down. There's little ridges in here. It's not smooth. It is definitely not smooth. There's little ridges in here that we leave a certain texture on the cast iron to actually take a head gasket and grip it. When your head gasket's sitting on here, it's designed to grip the head gasket and hold it in place. That's been working since day one. I mean, since the Model T, we've been machining things like this. On the aluminum heads, when they first came out back in the early 70s or mid 70s on the production cars, we were machining the deck surfaces of the aluminum heads the same as we did the cast iron heads, and that's not good. The reason being is aluminum expands more than cast iron. I mean, this head right here expands probably 2 or 3 thousandths. This one's more than double that. It expands 6, maybe 7 thousandths every time the engine warms up. Well, that means the head's expanding, contracting, expanding, contracting. When you have a surface like this that's not smooth, when the head gasket's sitting on there, it's like taking a draw file to it and just scraping away at the head gasket. Every time the head skates across it, it's eating up at the head gasket. So the first series cars, the production cars that were out with aluminum heads, they did have a problem. But I want to tell you, all the import cars that are out there and all the performance cars have aluminum heads on them. The reason we're getting away with that now and all the aftermarket heads is because we're machining them different now. If you look at this surface, it's almost like a mirror. You might see a little bit of texture to it, but it's not. It's smooth. The little discoloration you're seeing is just from the bits that go across, because these aren't cut on a cutter like these are. These are all CNC machined, and trust me, it's like a mirror. So what happens here is when the head expands, it just slides across the head gasket and does not disrupt the integrity of the gasket. It keeps it in place, and they last just as long as any cast iron head. I just wanted you to get a clue on that, and so you understand about that, and don't be afraid to run aluminum heads on the street, because they're the only way to go. All right, we're going to take this opportunity to show you 2 different types of Chevrolet heads. They are different. This one right here is a typical Chevrolet head. As you can see, all the valves are in line, and if we turn it, they're all at the same height. Very typical of most small block Chevrolet heads. This one right here is a little different though. This is very unique to one particular brand. This is made by TrickFlow. And if you notice, they're not all in line. And we'll turn it this way, they're not all the same height. They are different heights. These are canted valves. This is very unique to TrickFlow's own design. These are canted just like a big block Chevy would be, or like a 351 Ford Cleveland would be. The reason for that is that it puts the valve at a particular angle to help fuel the cylinder with more fuel and air, and we all know that that makes more horsepower. That's the whole name of the game, is filling a cylinder and getting a bigger bang. Bigger bang in a cylinder pushes the crankshaft around a little harder, makes more horsepower. Pretty simple. Let's look here at the valves in here. Kind of give you an idea. At first look, they look very similar, but we've talked about this before of unshrouding the combustion chambers. If we look here, you look in the valve area here, there's not a whole lot of distance between the valve and the combustion chamber on the edge of the chamber. We look over here, and in this chamber design and the way the valves are at particular angles, there's quite a bit of space between the edge of the chamber and the valve. So when these valve opens, they let more fuel and air into the cylinder. We get more fuel and air, makes a bigger bang and more power, just like I said. But that's 2 typical designs of Chevrolet heads. All right, while we're comparing heads, let's compare these 2 right here. All right, this is your typical small block Ford high-performance head. This one over here is your typical small block Chevrolet high-performance head. They both have the same valve size, the same intake and exhaust runner sizes. I mean, everything about them is very similar. The difference is Ford only has 10 head bolts that clamp the heads down to the block. Chevrolets on small blocks have 17 bolts. I mean, that's 7 more bolts, almost twice the amount of clamping force holding this head down to the block. With that, whenever you're doing like nitrous oxide or superchargers or really high compression, like 12 to 1, 13, 14 to 1, stuff like that, Fords can run into a problem with eating head gaskets. Let me show you right here. Here's the head bolt holes on a Ford. There's 10 of them. So there's 1, 2, 3, 4, and on down, 5, 6, 7, 8, 9, 10, okay? There's nothing in the middle of the head holding this area down. So what can happen is under extreme pressures, like I say, under nitrous oxide or superchargers, this area right here can cause failure in the head gasket. I mean, you can blow a head gasket pretty easily. Chevrolets don't have that problem. If you look at the area over here, you can see the head bolt holes here. I mean, they have them almost all the way around each combustion chamber, almost all the way around. Okay, so they don't really have a head gasket problem. Well, Ford, in conjunction with Felpro, have come up with a lock wire head gasket. This is a Felpro number 1006. What this is, it looks like a typical regular head gasket, but it's got a stainless steel wire inside here that does not compress. But anytime you put a head gasket on a motor and you torque the heads down, it actually flattens the gasket and conforms the gasket to between the block and the head. This has a stainless steel wire inside here that protrudes up. It does not compress. And the reason it doesn't compress is because on Ford heads right here, there are little 10 thousandths deep receiver grooves machined for what we call the O-ring head gaskets. What this does, it has a wire inside here that goes up and locks in place, and it just makes the head gasket a lot more durable, almost acts like an O-ring. So under nitrous conditions and things like that, it keeps the head gasket in place and less apt to blow. This right here is a new head that's available through Edelbrock. This is one that I actually, is my design. It uses a 70cc combustion chamber. Anytime you're doing superchargers, it's hard to find a set of pistons that get compression low enough. I mean, most of them are higher compression. So the way we can get a lower compression with most Ford pistons, aftermarket pistons, is with a larger combustion chamber. These have 70cc chambers, where typical of most Fords are 60cc. So this gets you a lower compression ratio. And with the O-rings on here, it's pretty solid against blowing head gaskets with nitrous and superchargers. Like I say, if you look in the Edelbrock catalog, you'll see right on there, concept by Badass Racing Engines, and that's us. This is a Ford head getting cut for the O-rings that the Felpro 1006 lock wire head gaskets use for nitrous or supercharged use. All right, we're going to do another head comparison here. These are two small block Chevrolet aluminum heads. I'm sure you've heard the term angle plug and straight plug heads. Those are two very important differences, and you really need to know what's going on with those. This right here is a straight plug head, and what that means is the spark plugs come straight out, just straight on out. This is an angle plug head. What that does is that you can see right here, the spark plugs are canted at different angles right here. What that does, if you look inside the combustion chambers here, it's just a design that allows the spark plug to be positioned in a particular area that burns the fuel and air mixture coming in much more efficient. And the better we burn it, the more power we make. There's a drawback to angle plug heads though. And what the drawback is header clearance. The header tubes come out, and doggone if it doesn't point these spark plugs right at one or two of the header tubes, and it's a real pain in the butt to get a spark plug boot on sometimes. So sometimes you got to weigh the difference of the power gain you make by going to angle plug heads and the pain in the butt factor you get on burning out spark plug boots all the time. So sometimes there's a trade-off. For every give, there's always a take. They do produce more power though, but it's not like light years difference, okay? Let me show you something here on spark plugs. All aluminum heads use long reach spark plugs. This right here is a long reach plug. I mean, it's got a lot of thread on it, okay? Aluminum's not near as hard as cast iron or anything like that. So they need more bite area, more bite surface area, so they have longer threads. One thing you need to know with aluminum heads, this one right here has anti-seize on it. That's the little silver stuff right here. What you need to know about aluminum heads is you have to use anti-seize on the spark plugs, or you'll never get the spark plug out. It'll go in once. By the time the head heats up and cools down and heats up and cools down, and you try and take it out, especially if the head's hot, you'll take the spark plug thread holes out with it too. So use anti-seize on there, and what it does, it just allows the spark plug to come out at another time. Speaking of spark plugs, let me show you something trivial here. Here's another one right here. This is something a lot of people make mistakes of. The aluminum heads always use a gasketed style spark plug, just like the early Chevrolets did. So they have a little aluminum or tin ring right here. A lot of people put these on backwards, and just for fun right here for trivia, the big side of the gasket, if you get a real tight close-up right here, we have a small side and a larger side right here. The small side goes towards the head. The larger side seats against the spark plug facing, okay, just so you know. All right, let's talk for a minute here just about combustion chambers and compression. I know this is on heads, porting, and valve trains, but heads do control the amount of compression that an engine has. So let me give you an idea what we're talking about. We're talking about the combustion chambers right here. You know, you've heard about 9-to-1 pistons or 10-to-1 pistons and stuff like that. Really, a piston doesn't dictate so much how much the compression is going to be. I mean, if you have a 9-to-1 piston so much, on a 64cc chamber, it's certainly not going to be 9-to-1 compression on a 76cc chamber. I mean, it's more area. I mean, what is compression? Think about what compression is. It's the volumetric area that the piston, when it comes up, is squeezing into the combustion chamber to make the amount of compression. All right? Well, obviously, combustion chamber sizes are going to dictate how much or how little the compression is going to be. Another thing that factors out is head gasket thickness. Sometimes, you know, on race motors, we use a copper shim gasket. Sometimes those gaskets are 5 and 8 thousandths thick. They're not very thick. On a typical motor, you know, a typical head gasket, they're 40 thousandths thick. Some companies make head gaskets that are 60 thousandths thick, 80 thousandths thick. It just depends. Well, we can dictate the amount of compression by the thickness of the head gasket and the size of the combustion chamber. Like I talked about before in the supercharger ready heads that I've come up with Edelbrock Corporation. Those have a 70cc chamber. Well, if we didn't have a 70cc chamber, we went down to the typical 60cc, we can't get the lower compression that's needed for superchargers. Well, the same thing you run into with Chevys. That's not just, you know, partial to Ford. So if you're trying to get a desired compression, and sometimes you can't quite get there with the combustion chamber size, you can alter it a little bit by the thickness of the head gasket. That just increases or decreases the height of the head and the amount of volumetric area inside the cylinder and combustion chamber. By the way, you know, combustion chambers are measured in cc's, and what that stands for is, you know, cubic centimeter, and we measure those in water. This right here is a burette. Basically, it's how we measure a combustion chamber or an intake runner or an exhaust runner. And what we do is, you know, we lay the head across here. It would lay down flat. We have an apparatus to hold that. We bring this on in. We put this over the top. Has a little bit of grease around it to make a little seal. We usually use a little bit of Vaseline or a little grease on here. And we simply fill it up with water. There's a little hole right here that we fill up. And the amount of water that this holds, we start on the burette right here. It starts with a 0. We fill it all the way up with water. As we turn the petcock on and drain water into here, we watch how much it comes down, and if it stops at 64 cc's, then they're 64 cc chambers. That's where that comes at. If it stops at 66 or 70 or 80 or whatever, that tells us the combustion chamber size. The reason we do that, you don't want one chamber, especially when you're porting, you don't want one chamber to be 64 cc's and then this one right here to be 68 cc's, because that decreases the cylinder pressure. That means this particular cylinder right here might be making 25 horsepower. This one right here might be making 20. Well, if they're all mismatched, the motor's going to be bumping and grinding and not making even power between all the cylinders. So we want to equal these out, and that's what we do. And that's why we want to know the combustion chamber size and why we want to make them even and stuff. All right, let's talk about head sizes now. I'm sure you've heard the term like 170cc heads or 185s or 210s, 220s. And what the hell are they talking about? Well, what they're talking about is the intake runner volume, and we talk about how we measure combustion chambers and things like that in volume as cc's, like cubic centimeters, and we measure that in water with a burette. So what they're talking about is, like on a stock head, it's about 145, 150 cc's in size. But let's give you a comparison here. Here's an aftermarket aluminum head right here, and this is a pretty high performance head. It's a 210 cc runner. That's a little bit big for the street in most applications, unless you're going pretty wild. Most aftermarket heads for performance use are 170cc, 185, stuff like that. If you're really going radical like Pro Street, 210, 220 is pretty good, but that's a car that's got like, you know, a 3,000 RPM stall converter and some 488 gears in the back and, you know, back halved with tubbed out wheels and stuff. You know, that's a pretty serious car. Bigger is not always better, that's for sure. Let me give you a reason why bigger is not always better. I mean, let's take this 210cc runner here. That's big for a small block, but on a big block, like a 532 cubic inch or a 614, that's micro-sized. The whole idea is velocity and flow. You know, on a smaller cubic inch motor, you don't want great big runners, especially on the street, because the velocity running through the intake runners here, the bigger you go, the slower the airspeed. And the slower the airspeed, the more sluggish the engine is. So sometimes you want to run a smaller runner, which makes the airspeed faster, just like a vacuum cleaner. If you have a shop vac and you put the attachment on the end of it with the small hole, boy, you could suck flies out of the air with that thing. But without that attachment on there, the airspeed going in is real slow. It's kind of the same thing. The engine's like a great big vacuum cleaner. It's drawing through here, through the carburetor, through the intake manifold, and right on down these runners here. So, you know, and the engine is only so many cubic inches, okay? So on a given amount of cubic inches, say 350 cubic inches, if we run a stock size runner, like a 150cc runner, the airspeed going through there to fill those 350 cubic inches is it's going to be pretty fast. If we put a great big head on there, the airspeed filling that's going to slow down because it's got so much area that it's trying to do, which makes the engine kind of sluggish. Hence why race cars launch off the line around the rev limiter sometimes. They have to be up in that RPM or they can't launch very strong. And the opposite of that, on a big engine, you certainly can run a larger intake runner and a larger head size. Another aspect of that would be supercharged applications. Anytime you're supercharged, or blown as they call it, you're forcing air and fuel through the heads. So that's a case where sometimes bigger is better. I mean, it's everything, there's a give to a take, but in most cases on superchargers, you can get away with bigger is better. The name of the game is obviously filling the cylinder, okay? If you got a bigger head, filling a cylinder you would think would fill it with more fuel and air, but that's not the case. The engine itself, the pistons and the cam profile is what's drawing the air in. The heads are just allowing how much to flow through and giving the airspeed. If the airspeed is too slow, the engine's going to be sluggish. If it's fast, the engine's going to have quick throttle response and good low-end torque for just pulling right out of the line. We all know that, 80% of the race is the first 80 feet. All right, while we're on the subject of intake runner sizes and head sizes and stuff, let's talk about something else that's very important. Let's talk about intake manifolds. This right here is your typical high-performance intake manifold. This one is by my friends at Edelbrock. This is a Victor Jr. right here. Very popular manifold for mild racing use and really hot street use. This has a 210cc runner that goes through the intake runners right here. All right, well, we certainly wouldn't want to match this to a set of factory heads that have, say, 150cc runners. That's a mismatch right there. This right here would be matched for 210cc runner heads. You want to keep the intake manifold runner size and the head runner sizes all the same for a nice smooth flow. Just as we wouldn't want to take a stock manifold and put it on large heads like this because you got a restricted flow. It's like trying to run around the block with your mouth duct taped shut and just trying to breathe through your nose. You can't do it. Your lungs are saying gimme, 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 and the intake manifold saying I can't flow that much air. Velocity makes flow, flow makes power. That's a rule of thumb. But you also need an ample amount of volume to go through there too. Again, I mean, you certainly wouldn't want to run around a block like that with your mouth closed. You can't get enough air in your body to support your muscles. Same thing, the engine needs a certain amount of fuel and air mixture to make power. If it's not flowing enough like that, you get too much manifold vacuum and the motor's not going to make its potential power. So everything's got to be matched. If you got a big manifold like this, run it with big heads. If you got stock heads, don't go buying anything like this and putting it on because you're not going to gain anything. You really didn't do anything. The heads are only going to flow what they can flow, no matter how big the intake manifold is. So keep things matched up and you'll make plenty of power. All right, while we're on the subject of intake ports and runner sizes and stuff, let's just look at some with a typical gasket right here. If we look down here at these ports, you can see this one is unported. This is just a stock gasket size right here. This runner right here is ported to the gasket. You see how nice shapely it is. I mean, it fits exactly perfectly to the gasket. Here's an aftermarket head over here, an aluminum head. And these come already pre-cut to match the gasket size. You put it right on there and it looks just about perfect, okay? That's called gasket match porting. All right, let's look at an intake manifold now. All right, what we have here is your typical high-performance aluminum intake manifold. A lot of you people probably think you can just pull one out of the box, bolt it on, and you get extra horsepower. And for the most part, that's pretty much true, but you're not getting the potential out of the manifold. On really high-performance manifolds like this Victor Jr. here, you take it out of the box, and I just showed you the head, how the gasket matched to the head. Well, look at this. Look how much space here needs to be opened up. This intake manifold is way smaller than the head that we just showed. So if you have aftermarket aluminum heads, they already come gasket matched. Intake manifolds don't. I mean, look at all this right here that needs to be taken out to match the heads. Now, mind you, the runners are 210cc on here, but they neck down right here because they know you're going to port it. I mean, all race engines and all performance motors, they figure you're going to port it, okay? And that's what we're showing you here is how to do this and what to watch for. So when you take a nice performance manifold like this out of the box and you bolt it on, you're not even matched to the head. So what's happening is you got this 210cc runner flowing down and it necks down at the last second and then goes into the head. That's not going to get you anywhere because this area right here is only going to flow so much, okay? You're not going to get much out of that. Let's show in retrospect here on a ported side. This side right here is ported. Let's show the same thing. Look at this. Look how nice this is right here. Exactly matched to the size. I've ported this right here just to show you what it will look like when it's all together. Now, This gasket right here fit those other heads that I just showed you a second ago perfectly. All right, now this manifold matches the heads. You got a nice smooth flow, no obstructions in the way. It doesn't divert air. I mean, it's just a nice even flow, fills the cylinder up, and like we said, fill the cylinder, more power. That's the whole name of the game. But let me show you something to not do. All right, let's pull the gasket out here, and you can look right here. Let me get my little pointer. See how nice and smooth this is in here? And we're not talking about smooth texture. I'm talking about smooth as in symmetrical, where the air is just flowing together, flowing right on out of the manifold, right smoothly into the head. It's a smooth transition. Look at this side right here. This is what I see coming to the shop a lot of times. People say, yeah, I got a ported manifold or a matched intake manifold. This right here is crap, all right? It does nothing. You can see it only goes in just a little bit right here. We're still small. I mean, here's the edge where the gasket goes right here, but look, we come in and it's still narrow right here. This does nothing. You need to go in at least an inch, inch and a half, sometimes 2 inches to get that blend and to get to the larger area inside here. Down inside, it is larger. When you come out here, like I say, they neck it down because they figure you're gonna port it, okay? Lesser performance manifolds like the RPM series manifolds and other brands of manifolds, for just basic street performance, they're already sized in a particular area, I mean, to pretty well match just basic performance heads. When you get into serious manifolds like this, like a Victor Jr. or a Super Victor or something like that, where the runners are 210cc, 220, 230cc, they know you're going to port the manifold, and they can't pre-do it because they don't know how big you're going to port it. I mean, a 350 cubic inch engine is going to be a lot different sized head runners and things like that than we might have on a 434 cubic inch small block, where we might run a 230cc head or something like that rather than a 210. So what we're trying to get at here is back over here to the nice ported side. This is what it should look like when you're done, okay? If it looks like this on this side here, this is not good, all right? Don't even bother. If this is what you're going to end up with, have someone professional do it for you, because someone just wasted their time. They didn't get anywhere with this. Make sure it's got a fluid-like flow and transfer of air from the intake to the head with no obstructions. This is all obstructive, and it's not going to do you any good. Not going to make any power that way. All right, we just talked about the importance of the intake manifold flow into the heads. Now, something every bit as important and a lot of times overlooked are the exhaust ports going into the headers or the exhaust manifolds. We just talked about the transition going from the intake into the head. Well, the transition going from the exhaust ports right here into the headers is every bit as important. Let's look at different types of gaskets and different sizes here. Here's a typical small block Chevrolet head. This is a deported exhaust. Chevrolet heads have multiple shapes. Some of them are square. Some of them are kind of an oval, some are round. I've seen heads with round ports on them before. Some oddball sizes. Here's what you run into. We have a deported here, which means the roof is raised and the floor is flat, which is great for flow. The high-speed area of the exhaust port is the roof. I mean, the gas is coming out here. This is where it's really flowing. The floor really doesn't do much. So we really need to pay attention to the top part here. So when you put a set of headers on, you want to try and match this as much as you can to the headers. I mean, let me give you an example. If you got headers with a square hole like this, it doesn't do much good to put a square gasket on something that's rounded on top. I mean, you've done all the work to the head, you might as well get the headers to match. So you go putting a square gasket on here, or a square port head, a square port header rather, all you're doing is obstructing the flow when it comes out. You didn't do any good there. Same thing here with a round gasket. You wouldn't want to run a round gasket either, because reason being is most of the time when you run a gasket like this, the headers usually are square or oval, and you end up with a deported exhaust or a square exhaust with a round gasket and a square header. You're just asking for a leak. Try and get headers that match your ports. If you're really serious about performance, you get a custom set made with a flange that exactly matches the heads, because it's just as important for what goes in must come out, and if it's going in fast, it's even going to come out faster and hotter. Very important. And same if you're trying to eliminate header leaks. You want to get a gasket that matches the same shape, or you're just asking for a leak. Here's the same thing with a Ford head right here. This Ford head has square exhaust ports. But look at the header gasket. This is a set of headers we got for it, and look at the gasket they sent us. And this is not even going to come close to sealing against here. This is a header leak waiting to happen. So again, just be careful of what you have there going on, or you're going to get leaks, and you're not going to get the performance that you wanted out of it. It's very important. All right, being that we're talking about runner sizes and things like that, let's just do something here for a little fun. All right, this is a typical small block Ford head right here, cast iron. It has a stock port size right here, and the one up above it, this is one of the heads I showed you before. We're taking the liberty of doing a little port work on it. Okay, let me show you something here just for fun. This is a big block gasket right here off like a 429 Super Cobra Jet type of a motor, that series of a motor. Look at the massive size of this against a stock port right here. I mean, that just dwarfs the stock port. Even look at it right here with a ported port. It's just not even close. I mean, you're talking, there's probably twice the amount of area right there. This next head right here, this is a 210cc, pretty much a race head, aluminum race head with 210cc runners. That's pretty big. Look at, it just dwarfs it. I mean, not even close to that. All right, let's see the same thing in a Chevrolet. This head right here is a ported out small block Chevy head. All right, this right here is a big block Chevy rectangle port gasket. It just dwarfs them, not even close to the same size. The reason I'm showing you this, I just want you to see the difference of flow between a serious big block head and some small block heads. Because you hear the saying where people say, oh, you know, I got a 347 Ford, or I have a 383 Chevy, all strokers, you know, and I got big block power and a small block package. Ain't gonna happen. You're not gonna outflow a set of heads like this that these go to, no matter what size it is. I mean, you got a big block Chevy that's 614 cubic inches. I don't care how big you make the small block, a 434 or a 454. You're still not 614 cubic inches. There's an old saying that really rings true here. There's no replacement for displacement. All right, let's do a quick overview of valves and just some basics of valves. What we have right here is an intake valve. Remember I said before, intake valves are always larger than exhaust valves, so they're easy to tell apart. This is just your typical iron valve right here. Nothing fancy about it. It's what you find in a stock engine. It's got the valve facing right here. This is what seals against the seat on the head. All right, we'll go over here to the exhaust valve right here. Same thing, it's just an iron valve with a big facing right here. That's what seats against the head. Let's go to a performance valve over here. This is a stainless steel valve. As you can tell, it's back cut right here. If you look, here's the stem, but they undercut it. Some people call it undercutting, some people call it back cutting right here, because this is actually in the area of what they call the bowl of the head, and fuel and air are trying to come down through here. So by narrowing this area right here, it unobstructs it and lets more air pass by. If you notice too, it's also thinner right here. If we go back to one of these over here, you can see what a tulip shape this is, how radius that is. We come back over this one right here, and it's very flat. I mean, just massive amounts of airflow going past here. All right, same thing with the exhaust valve. Here's an exhaust valve. Same thing, also stainless steel, back cut or undercut, as we can call it whatever you want. Nice little facing right here. And then we go over here. This is about the same thing, only this valve's made out of titanium. It's a lot lighter, takes a lot more heat. They're also a lot more expensive. But most street applications and even most race applications don't need titanium valves. This is NASCAR type stuff or really hardcore stuff. Same thing with the exhaust valve right here. Same thing, just a race valve. Of course, exhaust valves are not made out of titanium. This is different alloys of steel. Different brands use different alloys. They all have, you know, think this as an advantage over that one, and they're all good. I mean, for the most part, if you stay with a good name brand, you'll be just fine with valves. Let me show you a little trick you can do, and we're talking about valves, to get a little more power out of your motor without doing much to get there. Next time you're modifying your heads or you're getting a valve job done, ask for a 30-degree valve seat. And what that is, let me show you down here. We've got a couple of typical valves right here. Most valves have a 45-degree facing on them, and that's this area right here. That's what seats against the head. This is a stock valve right here, and it's got a pretty big facing. You look over here, here's a typical performance valve, and they're already back cut. We talked about that before. The stems are back cut, and the back of the valve is a lot thinner, but it still has a 45-degree angle right here at the facing. If we cut that to a 30 degree, so if we have a 45-degree angle, and then we cut it back at a 30 degree, that lays the angle down a little more. So when the valve opens, say at 300 lift, the valve is actually off the seat a lot more than it would be at 45 degrees. That just computes out to more flow, and more flow means more power. All right, this segment here is going to be on valve springs. I'm going to show you different types here, just some various common types of springs. This here is just a typical 1/250 spring. That means 1.250 inch. It's real common on like stock small blocks, Chevys and Fords, things like that. It's 1.25 inch in diameter. Just a standard wire spring, nothing fancy about it. This one right here is basically the same thing, but it's got a damper inside of it. A lot of people think this is a dual spring. This is not a double spring. This is just a damper, okay? This one right here, This is a bigger spring. This is more of a performance spring. It's a single, what they call a single spring. Obviously, you can see the wire on this is a lot thicker and bigger than this, and also the height of it is a lot bigger, and the diameter. I mean, it's a lot, just an all-around bigger spring. Why would you have a bigger spring? Higher RPM needs more spring pressure to close that valve faster. All right, and bigger valves tend to be a little bit heavier than a smaller valve. So on a big valved head, you need a bigger spring, and the more RPM you get, the more spring pressure you need too. This one here is just a single spring with also a little wire, flat wire damper inside of it. Let me go to the next one here. This is a double spring. In other words, there's a spring within a spring. All right, that just increases the spring pressure on it. It also has a damper inside. It's also a big wire spring, more pressure. Double spring, lots and lots of pressure. It means lots of RPM for a real high whine and race motor. Next one we have right here is kind of a sneaky way of getting away with a little bit bigger spring in a small spring seat. This allows you to run on a head that's only going to accept a 1,250 spring to run like a 1,450 retainer and larger spring wire here. What that does basically, it just gets you more RPM without having to machine the heads. This is what they call a conical spring. All right, while we're talking about valve springs here, we're going to talk about the measurements and the spring pressures of valve springs. First and foremost, all valve springs have to match to all cams. Meaning, you can't just get a valve spring and stick it on any cam, and you can't just take any cam and put it with any set of heads just because it has big valve springs or anything. What I mean by that is, say you have a flat tappet cam in your car right now, and you go buy a set of aftermarket heads. The valve springs that the heads come with probably don't match the cam. Every cam has a specific spring rate that it has to have for a closed pressure, meaning when the valve is closed, and an open pressure, or what we call over the nose, which is at the highest point of the lift on the camshaft. If those aren't matched, you can either wipe the lobe off the cam, or you can get valve flow at low RPMs or at a lower RPM. You won't be able to get the RPMs out of the engine because the spring won't close the valve fast enough. So there's different types of measurements we're going to talk about. First off, here's your typical valve spring right here. This is a resting height right now. The spring's just relaxed, it's just in its normal height. When we install the spring, and when it's installed, they have something called installed height. And what that means is when we put a spring on the head, it's actually compressed to a certain degree to a certain height from the bottom to the top. That puts a certain amount of load on the valve when it's in its closed position. If you don't have enough load on the valve or enough pressure on the valve to keep it closed, you'll get leakage at the valve and your motor won't run very good. Too much pressure at the valve and the camshaft might not be able to take it when it's an open lift. So all these have to be matched. So each spring will come with a set of guidelines as to what the installed height must be to achieve a certain closed pressure and what the given spring rate is over the nose of the cam or at full lift. So let's look here at installed height. Checking installed heights is pretty easy. What that basically is, it's the distance between the valve seat right here and the area underneath the retainer. Okay, and a fast way to do that is just take a dial caliper and just measure from here to here. But that's not the right way to do it. The right way to do it is with a micrometer. And here we have one right here. There's no spring in here. This just tests the distance between the seat and the underside of the retainer. And if you look right here, you can see this is up to a 2-inch. So right now it's at 1, and you can see the 8/20. So the installed height we would need a spring basically to go an installed height on this at 1/820. If we didn't want 1/820, say we wanted 1/800, we'd have to put a 20,000 shim under here to shim it up 20 more thousandths to get an achieved installed height of 1/800 to put the right amount of tension on a spring. The way we can test that, and the way you test springs, is with a spring tester. And this right here is a spring tester. So if you got older springs and you want to check them, or you got new springs, which even if you do have new springs, you should check them to make sure you have the correct seat pressure and for the correct installed height. Let's check here. This is a Rimac tester. We have a little scale over here, and we can find our installed height of any given number, whatever it is, and we can see the reading down here of what the seat pressure would be at the installed height. Then we come up and we would go, say, a 1/2-inch lift, so we'd move it down, say, a 1/2 inch, and we'd see what our given lift is right here, or given pressure is right here at full lift. And it's quite a bit. Average springs, stock springs, have probably 60 pounds at the seat and maybe 180 to 200 pounds over the nose of the cam. Race springs, some race springs have 200 at the seat and they're 500 or 600 pounds over the nose of the cam. That's why you can't put springs like that on a flat tappet camera. You will wipe the lobes right off the cam. All right, I showed you how to check valve springs with a Rimac tester, but you know what? That's probably not practical for anybody at home to have. This is an $800 tool. There is something that is practical though. Check this out. This right here is an on-head checker. It checks valve springs on the head. What it does is it just fits on a set of roller rockers right here. It grips the back side, right on the back there, sets on here, and we can just pull the spring to see what the seat pressure is. When we get the seat pressure, we can see the reading right here. It's 100 pounds, so we have 100 pounds at the seat. If we pull it down to a ½ inch of lift, we can see that it's got about, 190 pounds at a ½ inch of lift. This just gives us a value. It's fairly accurate. It's plus or minus a couple percent. It's not as accurate as a Rimac tester, but hey, if you're just checking just to be sure if you're in the ballpark or not, you can't beat one of these. Several manufacturers make these, and they're a fraction of the cost of one of these. And this is something you can throw in your toolbox and use every now and then. All right, another aspect of valve springs we need to talk about here is coil bind. You've probably heard of that term before. I'm going to explain it in real simple terms here. Basically, what coil bind means is when the coil binds up or bottoms out on the spring. And what that means is, right here we have a rocker arm that's at the base circle of the cam, meaning it's not up on the lobe of the cam, it's on the back side. So this is how the spring naturally sits at installed height. We have lots of space in here for the spring to be able to compress. All right. Well, as we can see with this one right here, this is on the nose of the cam and at full lift. So if this is like a 520 lift cam, then the valve is depressed 520 thousandths of an inch, or 20 thousandths more than a ½ inch. What we need to be sure of is that when it's at full lift, we have ample clearance in here so the coils don't bind and the spring could break. So what we need to do is just take a feeler gauge and just make sure we have at least 60 thousandths clearance in there. 60 is a pretty standard that you want on both intake and exhaust valves. If we don't have that, like I say, the spring will bind together and things break when that happens. So just be sure you have enough clearance here. The next thing we want to talk about too, on the same subject, would be the distance of the installed height and the compressed height. Valve springs, aftermarket valve springs, are taller than a stock valve spring, so they allow more movement. For instance, like this right here, we have probably 75, 80 thousandths of clearance in here. If this was a 600 lift cam, we'd surely bottom the spring out and the spring would break. We'd end up with coil bind. So you want to be sure that the springs allow enough lift for the cam that you're using. If you do that, you'll be all right. All right, the next thing on the hit list here are retainers and locks. What the retainer is it's what holds the valve spring in place with the locks on the valve, keeps the spring in place here so the valve can actuate up and down. Basically, it looks like this. We have the locks, and you have the steel retainer with the valve spring, and that keeps it in place. If these aren't strong enough or they fail, it all lets loose, the valve drops down, everything breaks, the valve goes in, and Mr. Piston closes the valve for you. Not a very good scenario. These are factory ones right here. This is just made out of steel. They're a little bit heavy, okay for a mild motor, but you certainly don't want it on a real performance motor. On a real performance motor, you're going to want alloy steel ones. These guys right here are made out of a chromoly steel. They're a little bit heavy, but they're certainly strong. And of course, we use a stronger lock to hold the retainer in place on the spring. Because on performance motors, you're definitely going to use a stouter spring. This is a double spring. It's got 5 times the tension of this spring right here. So anytime there's more spring pressure pushing up, you're really pushing up on that retainer, and the strain is all on these locks. And if it can't stay together, the retainer pops off, and again, like I said, the valve drops down and Mr. Piston closes it for you. Not a real good scenario. Next, we have a titanium retainer. These are about 25% of the weight of these right here. Super lightweight. And we all know now that the lighter the weight is over the tip of the valve, the less spring we need to close it. And that's a good scenario. Serious things like these, titanium retainers and serious race engines, they use a different type of lock. As you can see, these are a lot larger compared to these right here. These are a 10-degree lock. These are a 7-degree lock. They're quite a bit thicker if we compare them in size here. Reason for that is higher spring pressures. Race motors that have big spring pressures need big-time locks to hold everything in place, or again, they'll fall off and break, and you have a catastrophe. All right, now we're going to talk about rocker arms. What we have here is a lineup of typical rocker arms, everything from a stock one on up to a full-on race rocker arm. We'll take you through these here from a stock one here. This is just your typical stamped steel rocker arm you find on any stock car coming off the assembly line. It's made out of stamped steel, nothing fancy. It's got a little pivot ball inside here where the rocker stud comes through so it can swivel back and forth and actuate the valve. On the back side here, this is what rides against the valve tip right here. And right here, of course, we have a pocket for the push rod to go inside. Nothing fancy about that at all. Here's the same thing for a Ford. You can tell it's a Ford because you flip it over, it's got little rails right here. Most Ford heads don't have pushrod guide holes where Chevys do, so they use a little rail here that keeps it centered over the valve tip. We'll move to the next one here. This is the next generation up. This is a roller-tipped rocker arm, not to be confused with a true roller rocker. It's made out of stamped steel. As you can see, it's quite a bit thicker than some of the others. It's also quite a bit heavier because it's pretty well made. It's a lot heavier duty steel. It does have a roller tip, so when it rides across the tip of the valve, it glides rather than scrapes across like which one of these would do. It ends up just scraping across the valve tip. This takes a little bit of friction away. But unfortunately, that's not where all the friction's at. Friction's really down inside here into this rocker ball area. And I'll show you that next here. This one's for a Ford. We can tell that again because it's got the rail area there, what they call for rail rockers inside here, that glides across or keeps it centered across the valve tip. This one right here is your typical Chevrolet one. It doesn't have that rail system. Chevys don't use that system. Again, it's stamped steel. This is a little less quality. This is one of the mass-produced ones. It does have a roller tip, uses the same type of ball. These are all right. They're okay for a street motor, nothing great though. Then we jump up into a true roller rocker arm. These are made out of aluminum. This is a low-line one right here. These are quite a bit less expensive than the really good ones. They're made out of a okay aluminum. I wouldn't recommend these for on a serious race motor or anything with real high spring pressures or anything. I mean, these are bargain-priced rocker arms, and you get what you pay for as always. All right, but the advantage of this is it doesn't use a ball socket inside here. It uses a needle-bearing fulcrum right here, and this is where all the friction's at. Contrary to what people think, it's not on the valve tip right here. Although, it does ride across the valve, and if you don't have a roller here, I mean, it does beat the heck out of the valve tip. But this is where all the friction's at, right inside here. Another advantage you have to these is stability. We'll go to this one right here. This is the next generation up. This is a better rocker arm. It's a little thicker, made out of really good aluminum. This is a T6 aircraft quality aluminum. A little bit better quality than this one. Again, a roller fulcrum right here and a roller tip right here for riding across the valve. All the real good ones have chrome moly push rod inserts inside there. A little bit better and larger fulcrum area. And if you notice on a roller rocker, these can pretty much only move up and down. They can't really wobble side to side. We'll go back here to this one here. This is a roller tipped rocker that does use the ball socket inside there, and it does allow them, as they're riding up and down, they can also twist back and forth. We do have movement there. That's not real good. That's not really desirable. I mean, you certainly don't want that kind of movement at 7,000 or 8,000 RPM. That's just not doing much good for the valve assembly and the valve train. When this rocker stud is attached inside the head, these don't really have side-to-side movement. They can only move up and down, which is a good advantage. I mean, it keeps everything stable and keeps parts moving in the direction they're supposed to be moving. This one right here is the next one up. This is a little bit better quality. It's a little thinner aluminum because it's a better quality. They're able to shave more mass off because it's a stronger aluminum. It's aircraft aluminum. It's real good. Again, a needle fulcrum, a roller bearing on the top, and a chrome moly insert for the push rod. Really good rocker arm. We use a lot of these on our motors. This one right here is a very common one also. It's even thinner yet, lighter weight. This is a really good rocker arm, but you can see it's got a little problem. This is one that had a little problem. When we get into valve train geometry later on in the segment here, we're going to show you why this happens, because someone didn't set up the valve train geometry very well. What's happened is the rocker arm was going off the face of the valve, off the very tip of the valve, and it just ripped the roller right off. And this can happen if you don't check things like push rod length and valve train geometry. I don't care how good the rocker arm's going to be, it's going to fall apart. And that's not good. Let's go to the next one here. This is 4340 steel. This is a really good rocker arm. Now we're getting up into some good stuff. Steel is heavier than aluminum, and there's no doubt. This overall weight of this is heavier. The difference is, though, look how thin it is right here. I mean, look at the mass here on these, comparatively, how wide it is here or how wide it is here, and how thin this is. This is able to put less weight over the tip of the valve. And if the valve spring isn't trying to push up on a heavy rocker arm, it's only trying to push on this little lightweight area. So the area over the valve and the valve spring is a lot less, which means it takes less valve spring to push that back up at a higher RPM. Get more RPM out of these. It's really super strong. It's very rare that you're going to break one of these, even with valve train problems and geometry problems. These usually survive. I'm going to go to the last one here. This is as good as it gets. This is shaft rockers. These mount down. They don't use a stud. I mean, these mount flat on the head. They have no side-to-side movement whatsoever. These can only go up and down. They have needle bearings inside here, but they're mounted on two side studs on a shaft that goes through. And these things are stable. I mean, these things would take just about any RPM. This one has a few advantages. It does have a roller here. These have needle bearings in the rollers rather than just an axle with a wheel stuck on it. These actually have needle bearings inside here. There's a little feature on this too. If you look right down here, there's a little teeny hole right there. That's called an oiler. And what that does, right here, you know, obviously the valve is sitting under here. Also the valve spring is there. On extreme motors like, you know, motors that run circle track or road courses and stuff, they're at 7, 8, 9,000 RPM continually. I mean, they're like that for hours sometimes. Well, this poor thing's going up and down, the spring's going up and down, and anytime you take metal and bend it, like squish a spring back and forth all the time, it creates heat. Well, what this does right here, oil squirts out of this hole, and actually oil quenches the valve springs and keeps them cool. So at extended RPMs for long periods of time, the valve springs stay nice and cool and actually function a lot longer. Speaking of shaft rockers, let's go to this motor right here and I'll show you this. This is a race motor we're building for a customer of ours. These are excellent rockers here. These are good as they get, really. I mean, these are Jessel shaft rockers. They're real pricey, but I mean, you get what you pay for. It's again one of those things. This is an extreme motor that runs road courses. This motor's run season after season at extended RPMs and has never placed less than top 3 in the circuits it's run in. Came back in for a freshen up. We're just going to send it right back on out and let them kick some more butt and win some more races. This is the same design as here. I'm going to pull these off. I happen to have these loose off here. We'll pull these off right here and set them down. These also mount on a shaft right on through. So again, there is no side-to-side movement at all. These can only move up and down, which keeps the valve train stable. And you got larger needle bearings in here. And again, these are needle bearinged also. These are not just an axle with the wheel on there. These are really good setup. They're also, like I say, quite pricey. These are not recommended for like your mild street motor, your 400 or 500 horsepower motor. It's pretty much overkill unless you're going to be running like a road circuit or something like that where you're going to be at 6,000, 7,000, 8,000 RPM for an hour at a time. You know, like running the Silver State Classic or the Bonneville 100 or anything like that, or road courses lap after lap. All right, let's put these back on so don't forget about them. All right, you notice these mount by pairs on here, sets of 2. They do that all the way across the shaft. They're mounted on one common mounting bar here. The reason they do that is so it comes on and off very easily. In the middle of a race, if you have to change a rocker or something like that, which is rare with these types, but if you did have to, the whole assembly comes off. You put it back on, it's a quick adjustment, and you're ready to rock and roll again. You're in and out of the pits. Let's go over here and talk about rocker-arm ratio a little bit. And that's a really gray area where people just don't understand. Basically, on a rocker arm, a lot of them are stamped. We can get a close-up here. Maybe we can see. Right here, there's a 1.5 on here. What that stands for is the ratio on here is 1.5, meaning that if the cam lift is pushing up 300 thousandths of an inch, okay, that means it's going to times that by 1.5 from here to here. So it's 1.5 times that amount. Okay, so it would be 450 thousandths inch lift. All right, so if the rocker arm pushes up 300, it's pushing the valve down 450 because that's 1.5 times. All right, let's go to the next one here. This one here, as we can see, has a 1.6 ratio on it, stamped right on it, 1.6. What that means is the same thing, 1.6 ratio, meaning if it pushes up here, it's timesing this from the center line to the end of the valve tip here times 1.6. The reason there's different ratios is some cams you might not be able to get the lift out of it that you would normally want. So let's say you have a motor and you like the cam but you want to wake it up a little bit, and you can only grind a profile on a cam to a certain extent. You can't just automatically put more lift in a camshaft, and sometimes changing a cam is a royal pain in the ass. So what you might want to do is just change the rocker arms. So if you had a 1.5 rocker like this, and that say gave you a 450 lift, and you go to 1.6, I don't do the math in my head right now, it'd give you like a 475 lift, another 25 or 30 thousandths lift, which will push the valve open a little more, fill the cylinder a little more, give you a little bit more power without changing the camshaft. All right, let's go to the next one here. This is the same thing. Here's that broken rocker where someone had some geometry problems. Sometimes I save battle-wounded things like this for customers when they come in. I can show them, hey, look, this is why you want to know what the heck you're doing, because if you don't, this is the kind of stuff that happens, and this was a good rocker arm. This was a very fine rocker at one time, but someone didn't put the motor together good, and that's why it came into us, because they couldn't figure out why they had problems. And it was a simple push rod geometry problem that was going on. But this one right here, we look right here, it'll say 1.7. We can get a little tight shot of that right there. It says 1.7 right there. That's telling us the ratio of this rocker is whatever the cam lift is times 1.7 here, all right? Now you'd think, well shoot, if I got 1.5s in my car, I'm just going to put 1.7s in there and make the cam have a big lift. That's not always good. Reason what happens is, how it increases the ratio is it brings the push rod closer here. So let me give an example, like breaking in a camshaft, sometimes we use a 1.2 ratio rocker, which the push rod's way out here. It takes the load off the camshaft. I mean, this is a lever. Imagine if this was real long out here. It doesn't take much to move it back and forth. It's just like a pry bar on something. So if we're trying to pry something up and we had a long bar, it's easier to push out here. The closer we get closer to the pivot point of the pry bar, it's harder to push. Well, the push rods go through the same thing. If it's out here, it's an easy cantilever system. As it gets closer and closer and closer, it takes more pressure to push that up, to push this valve down here. So what that means is, on a typical flat tappet like a solid lifter cam or a typical hydraulic lifter cam, puts too much load on a cam. You can wipe the lobes off, or you increase the lift and you don't check things like piston to valve clearance or coil bind, where the, valve springs can only compress so far before they bottom out. If you bottom a valve spring out, it's coil bind. If you get coil bind, the valve spring breaks. Okay, I mean, there's no doubt about it. So you can't just take big ratio rockers and stuff them on a stock motor and say, hey, I'm ready to rock and roll, because you're just going to have problems. So you want to stay within reason and not have problems like that. All right, we talked before about installing Chevy valves in Ford heads, and that's an okay thing to do for performance, being that they have the same valve stem diameter sizes. And as long as you unshroud the chambers, it's okay to do. There is a problem that you run into, though, with the rocker arms on these. Ford valves, if we look right here, Ford valves have a tall stem. Chevy valves over here on this head, these are Chevy valves also on a Ford head, have a shorter stem right here. You can see the height between the retainer and here to the valve tip, as opposed to this retainer here. It's a lot taller. Well, remember I explained earlier that Ford uses rail rockers on most of their head designs. Well, if you look right here, down in here, Ford uses no guide plates. Well, the way they keep the rocker arm centered over the valve is by these rails right down here, which keeps it centered right over the valve so it can't go anywhere. So when the rocker arm comes up in and sits in here, the valve can't move anywhere. It stays, it can move up and down, but it can't slide off the tip of the valve. This is a roller tipped one. This is a factory one, same thing. It's got little rails on the side to keep it centered from falling off the tip of the valve. Problem with this is, when we install Chevy valves in a Ford head, we take these over here, drop it on here. These side rails here hit the retainer. They don't push on the valve. Let me get a better view here. I'll take this rocker and put it on here. You can actually see, if you look close there's a gap. It's not even touching the tip of the valve. It's touching the retainer. What happens is, if you do this, when the push rod comes on up in, goes through the guide plate on here, wants to push down, it pushes the retainer. So what happens is, the retainer pushes down, the valve locks come out, the valve drops down, and a piston comes up and smacks it. You got to be careful with this. Anytime you put Chevy valves in a Ford head, you got to go to a Chevy rocker arm, which is this right here, typical Chevy rocker arm. Reason you can't use Chevy rocker arms on Fords is because, again, Fords don't have guide plates or push rod guide holes. Chevrolets do. In the factory heads, they have very small guide holes that keep the push rod located in line with the valve. Fords, they don't. So if you take a Chevy rocker arm and you put it in a typical Ford head, there's one right here, there's nothing to hold it in line. I mean, this push rod can go back and forth, and look what happens. This is what happens. The engine will run for about 3 seconds. This comes off. It pushes the retainer right here, of course, releases the locks. The valve drops down into the cylinder. I mean, it's a catastrophe, a big-time catastrophe. It just can't happen. A lot of people make this mistake. You really want to be careful with rail-type rockers on Ford heads and non-rail-type rockers. Let me show you something that's not the thing to do. This is your typical stock one that someone had before, okay? I save little things like this, like I explained earlier with the other rocker arm missing the wheel. This is something else that I saw come into the shop one time that some idiot had done. They had Ford rail rockers on their motor. They put Chevy valves in, and to get away from it, they took this rocker arm and they stuck it on a grinder and ground it down. Don't do that, okay? That's just lame, all right, totally. That's not what you do. Get the right rockers for the right job. One thing, Chevys use a 1.5 ratio rocker most of the time. Fords are 1.6 factory, okay? So already you can have coil bind problems, too much lift on a cam, maybe a little piston and valve clearance problems, because that's another 25, 30 thousandths extra lift that you're going to get out of that. But this is hokey, man. You don't want to do that. Besides, even this, it's probably still, if you can see right in there, it's probably still barely touching the valve tip. It's still touching the retainer. So even doing this hokey job, that didn't fix the problem. Don't do stuff like this. All right, well, as far as rocker arms go and rocker arm ratios, we've talked about that before. Here's a 1.5 right here. You can see it right on the rocker arm. It says 1.5, and this one right down here says 1.6. So this is a small block Chevy head right here, and 99% of all small blocks use a 1.5 ratio rocker arm. Of course, in performance applications, you might want to increase the rocker arm ratio to 1.6 or 1.7, sometimes on just the exhaust valve, sometimes just on the intake valve, sometimes on both. What that would do is increase the lift of the valve and not really mess too much with the duration or anything like that. It does actually increase duration a little bit, contrary to what people say. It will increase the duration by 1.5 to 2 degrees. It doesn't mathematically, but in reality it does. There is a little tool that cam manufacturers use called an Optron, and basically it's a strobe light. And when they're running the engine at a very high RPM under the strobe light, they can actually measure more duration, even though it's not mathematically in the camshaft. You haven't changed that. All you've changed is the lift. But just so you know, it does change it about 2 degrees. It adds about 2 degrees to it. But what I want to talk about here is increasing rocker arm ratio. You can't just pop a set of rocker arms on there and say, oh, I'm going to go with 1.6s. There's a couple things you really need to know. Anytime you increase the ratio of a rocker arm, let me show you here with this guy. The push rod sits up in the saddle up here. If we're going to increase the ratio of this rocker arm, the length from here to the tip never changes. It's the length from the center to the push rod that changes. So increasing the rocker arm ratio, we're going to move the rocker arm or the push rod closer inside. That puts more of a load on the camshaft, but less movement here means more movement over here. Okay, so it just increases the ratio. So if we go to a 1.6 rocker right here, automatically the push rod cup is moved forward. Well, the problem with that is on the heads right here, if we look down in here, the push rod guide holes in a factory head are only designed for a certain ratio rocker. I mean, Chevrolet didn't intend to have 1.6 or 1.7 ratio rockers on their heads. So you can't just go stuffing a set of 1.6s on a stock set of heads and expect it to work. So if we look down in here, here's one, this is that head that I've modified before and done different stages, and this one right here has the guide plate. If you look real close down here, you can see down in here that the push rod guide plate holes are enlarged. The original guide holes are enlarged because we're not using those anymore. We're only using the guide plate. Or if you look over here, they still exist in the factory form. So what we would need is to enlarge those. There's a real easy way you can do that. It's with what they call a Lewis tool. And this is a Lewis tool right here. Very simple little tool. It's made out of steel. It has an offset side on one side and it's open on the other. This is real easy to use. What it's designed to do is you drop it in right here, and what that'll allow us to do is take a drill, run it right down inside here while that tool's on there, and drill out What that did was elongate our hole right here. This allows the push rod to come closer to the rocker arm and have more space in here to move. The Lewis tool is real easy to use. It only costs a few bucks and you can do that yourself across the head there. All right, I wanted to show you this little tool here. This is a stud removing tool. There's a lot of you out there that just have to do stuff yourself, which is great. I mean, I like that. That's what you want to do. Sometimes when doing stuff like this, it's better to send it to a machine shop and let them do it with their heavier duty tools. But you can do it with this. I've done it with this when I first started out many times, and it does work. It's as simple as it gets, but it does work. I'll show you how it works and what it does. It is for removing studs. There's a little locator pin right here. This will come off. That fits right over the stud, just like that. Put a little stack of washers on there. Make sure you get a grade 8 nut. You want to put a grade 8 nut on there. Pop that on there. That's a 3/8 nut right there. So take an impact gun with a 3/8 impact socket on there, you put it on there and brrr, blast it. And what that'll do is this tightens down, it lifts the stud out of the head. You might have to go back again and put a couple more washers on there and stack it, but as you're tightening this nut down, it's pulling the stud out of the head. This is a hardened piece of steel right here, so it's not going to mar or move or distort or anything. When the stud pulls out, we will be able to drill it and tap it. All right, now that I've pulled both the studs out, this is where this little pin comes in handy. You can see both studs are out. We drop this pin in. What that does is it locates this piece of steel right here directly over this hole right here. So I can take a 7/16 tap, a coarse thread tap, run it down inside here. And what this does is it guides it into the hole, straight into the hole. So I can run it right on down in. And then we can tap it. And what that does is it taps this hole out. So when we're done, we pull it out. We can pull everything out of here. Of course, I already did this one when you weren't looking. And we have screw and studs. There's a screw and stud. Now mind you, it's not a shouldered stud like this. The advantage of this though is when you put these type of studs in, you have to machine the bosses off here, off the head. That's a little bit of extra machine work. This right here, you don't have to do anything. You just pop these on. Of course, you can't use guide plates, but just for a quick way to put screw and studs in, that way you can run a bigger camshaft and not suck the studs out of the head. That's a quick way to do it. All right, what we have here are various types of rocker nuts. The nuts that we use on rocker arms are a self-locking style of nut. In other words, they go on, but like at the tops right here, they're pinched a little bit, so they go on kind of stiff, so they can't back off. Problem is, on factory styles like these two right here, sometimes they do have a tendency to back off. So what we use are these right here. When you buy a set of roller rockers, you get a set of these. These are called poly locks. And what these are right here is you can adjust them with a wrench. Once you have the rocker arms on there, you can adjust them for the correct lash wherever you want it at, and then you can put an Allen wrench in there and give it a cinch, and that holds it in place, so it will not back off. Another thing you can do is just get a little nifty tool like this right here, where it does the same thing. It's just all in one. So you can adjust the lash that you want to 0 when we show you how to adjust valves. You'll be able to use something like this, go right on in there, set it, done. That's just adjusted. Another variable type right here, this is a Ford style right here. We talked about this head earlier where these are non-adjustable. As you can see, it's a 3/8 stud pressed into a typical Ford head. A lot of Fords had these where it necks down the 5/16. These are non-adjustable. What happens is this nut right here goes on freely. So it goes all the way down, it torques to 19 to 24 foot-pounds and stays. That's kind of a bummer because you don't have an adjustable valve train that way. Like you can't run a roller rocker or a better set of rocker arms. What you can do though is get a set of poly locks. Now these aren't very common, but they are available. And what these are the same thing as the poly locks over here, but they're in 5/16. You can find these by different manufacturers, and it does the very same thing. You can adjust it, cinch it down, and you're done. That'll give you an adjustable valve train and a non-adjustable rocker stud for Fords. All right, this is another type of rocker nut right here. As you can see, it's a little different looking than the other ones we just looked at. This right here goes on and you adjust it just like any other valve. It goes on. You can adjust it when you're done with a simple wrench just like this, like I showed you. You set your lash, lock it down, and you're done. The reason these look like this though, this is because this is a stud girdle system. And what that is, here's a billet aluminum stud girdle that goes on here. And what this does is it ties all the rocker studs together. Basically what it does, it prevents studs from breaking. When you increase the lift on a cam, like you go to a real high lift cam or you're going to very big valve springs, it puts a tremendous load on the studs. I mean, the only thing holding the rocker arm in place are the studs. Well, every time this valve over here gets pushed down, all that spring pressure is being loaded on this stud. When you put a stud girdle on here, it disperses that load across all the rest of them. So if this stud's going to pull out, it's going to have to pull this one, this one, this one, and this one with it. That's just impossible for it to do with this on here. So once this is in place, and you simply take a wrench and tighten it down on here, that locks it in place, and all the studs are tied together and makes it much more strong. All right, let's show push rods now and the different types and styles that are available in most applications. This right here is a typical stock push rod. Nothing fancy about it, it's just mild steel. It's got rounded ends on it. That's what you'd find in a stock motor. Next one over is just the next grade up. It's also mild steel, which you'd find in a stock motor, but it's got welded on tips that are actually a little bit better quality and more desirable than just a low line rounded end one. The next one over we have is chrome moly. But this is a lower line chrome moly one. The reason we can tell that is because it's got pressed in tips on here. These are chrome moly tips pressed into the tube. There's one at each end. And typically that's not something you really want in a really high performance motor. It's just more apt to fail. The next one over is a one-piece chrome moly push rod. This is the way to go. These are typically 080 to 083 wall, and what that means is the wall thickness of the steel is 80 thousandths to 83 thousandths, which is substantially thicker than a stock push rod. let alone being made out of chromoly, which is a very strong steel. Usually you can tell a chromoly too because they're black oxided on the outside. Where you look at a stock one right here, they're usually just a natural steel color. Let me show you here too. We have a pushrod guide plate off of a head. And anytime you have a set of heads with guide plates, like if you're modifying yours or you purchased a set of heads that come with screw-in studs and guide plates, you must use chromoly pushrods because the pushrod itself rides through the guide plate. And as it's riding through, it's creating friction on the sides of it as it's trying to keep the rocker arm centered over the tip of the valve. If you don't use chromoly pushrods and you use a standard pushrod, this is what happens right here. As you can see, someone tried using a stock pushrod with a guide plate, and the pushrod is just not strong enough to take it, so it wore right on through. A few seconds longer, this engine would have failed. Next one we have over here is an adjustable pushrod. It's not something you'd run inside of a motor. When we're checking valve train geometry, this is what we use right here, and it basically screws together and screws apart, so you can increase and decrease length by screwing it. What it does right here is every time you turn this one full rotation, that's 50 thousandths. So if you do 2 rotations, that's 100 thousandths. Reason we do this is you can't just order a set of stock pushrods for a motor, like say a small block Chevy. You can't say, well, I need a set of pushrods for a small block Chevy. Reason being is, what if we deck the block 30 thousandths? And then what if we shave the heads 20 thousandths? Well, that's 50 thousandths difference. That means the head and the block, everything now is sitting lower on there, which makes the pushrod appear longer, all right? What if you bought aftermarket heads that are aluminum, where aluminum's thicker? Now the head sits taller. So the pushrods are never a standard length. We always need to check with an adjustable pushrod like this to get the correct geometry. Incorrect geometry on a motor like that can cause all kinds of problems. That's pretty much pushrods in a nutshell.